This is a parity problem. We want to count the number of k-limited permutations and prove the number is odd or even under very specific cases. So how do we do this? The main idea, if we ever have to prove something is odd or even and we don't have a closed form, and it doesn't look like we can get a closed form here, is to just start canceling off everything in pairs of 2. Or you can split the whole set into 2 and then use a bijection between the 2 parts. What's the first thing that you notice? Well, if a permutation works, then so does its inverse. So we can just cancel off each permutation by just pairing it with its inverse, and that just leaves permutations whose square is the identity. There's not a lot of them, but they're easier to handle. But then we have to keep going. We're gonna have to, if we look at permutations which are order 2 or less, then we can try cancel off by looking, say, where does 1 go A, where does 2 go B? Well, 1A, 2B. We interchange that with 1B, 2A. We can, unless B is equal to k plus 2, because then it's no longer k limited. So we can't make this exchange. And then no problem if B is equal to k plus 2. Let's look at whatever 3 goes to. We try the same thing. Well, there's a problem if this thing is bigger than k plus 1. That's another issue. Can't be k plus 2, but there is an issue if it's k plus 3. Well, we keep going, and we see, well, this can't go on forever. If we get up to k plus 1, and then 2 goes to k plus 2, 3 goes to k plus 3, all the way up to k plus 1 goes to k plus 1, then 1 has to go to itself. This set gets sent to itself, and then we basically have a permutation of n minus 2k plus 1 elements. But we've reduced the problem to a smaller case. So let's see how this solution gets written up formally. First, we let Sn be the number of k-limited permutations of n that have order less than or equal to 2. We let S0, 1, and Sm is equal to 0 for m less than or equal to 0. This is so that when you have something like Sn minus 2k plus 1, it makes sense. That's a negative number. Then we do the whole thing of proving if sigma is k-limited, so is its inverse. You see, if you plug in the inverse here, as in terms of I, you get this. That's your proof. So now we're down to focus on Sn. And how do we define this swapping formally? Is that we define it in terms of a parameter S. Ts is a set of permutations for which I gets sent to I plus k for 2, 3, 4, all the way up to S. And then S plus 1 does not get sent to S plus 1 plus k. It's the one element that we get to swap. So then we define the function fs on the set intersection Sn of Ts to itself by this, which is cycle notation. Now we have to check that elements of Sn intersect Ts actually get sent back to the same set. We have to check this is an involution, and we have to check that there are no fixed points. And that will prove that SNTS is even. So first, clearly no fixed points, because we have a different permutation here. Sigma of 1 is not equal to sigma of S plus 1. Now next, we have to check it preserves k-limitedness. That means it's still in Sn. We can see sigma of S plus 1 is less than S plus 1 plus k. Can't be k plus 2, can't be k plus 3, all the way can't be k plus S, because 2, 3, and S already cover that all the way here. And this is and because also the permutation is order 2. So if sigma of I is I plus k, then sigma of I plus k is I. Then we check, obviously, this is also preserved by k-limitedness, just because 1 is really small, and that shows that k-limitedness is preserved. how do we show this permutation is still in TS? Well, sigma of I is still I plus k after we apply a function to this permutation. This permutation of permutations really is what Fs is. And then s plus 1 gets sent to sigma of 1, which is not equal to s plus 1 plus k. So the parameter s is preserved. So finally we have that this set is, the size of this set is even. And what about the rest of the permutations? Well, like we said in the motivation, the rest of the permutations, we can see that sigma 2 gets sent k plus 2 all the way to sigma k gets sent to 2k, k plus 1 gets sent to 2k plus 1, and 1 has to be sent to 1, because consider the element that 1 gets sent to A. Well, A can't be any of 2, 3, 4 all the way up to k. Can't be k plus 1. And if it's anything larger, that violates k limitedness of the sigma, so 1 has to be sent to 1. Everything else is already covered. So this set is sent to itself, and the number of such permutations in Sn is clearly Sn minus size of Sn minus 2k plus 1. Because we are just working with the other n minus 2k plus 1 elements. The bijection consists of just chopping off the first 2k plus 1 elements of the permutation. So then we have the congruence Sn is congruent to Sn minus 2k plus 1 mod 2, and we could just use induction. We could write n is equal to a 2k plus 1, a times 2k plus 1 plus b, and use division, whatever you want. But then using S0, S1 is 1, and Sm is 0 for m less than 0, we get the result.